For centuries, the university model relied on passive information broadcasting. Today, it fails to bridge the gap between delivery and actual retention. Delivering a dense, perfectly accurate lecture does not mean that information is being encoded. High-density data transmission does not automatically translate into a structural change in how a student understands a subject. This gap becomes visible when a student recalls a theory for a test but cannot apply it to a practical problem. That failure isn't necessarily a lack of effort, it's a breakdown in the cognitive processing sequence. To bridge this gap, the professor's role shifts from a broadcaster of data to a designer of conditions, someone who engineers the environment to trigger specific mental operations. Robert Gagne's 9 events of instruction maps 9 specific gates that information must pass through to enter long-term memory. The framework aligns external teaching stimuli with internal neurological stages. Each gate represents a mental event that must be triggered in order. Conventional teaching often focuses only on 1 or 2 gates, typically the delivery of content, while ignoring the subsequent processing required to make that content stick. Because these events mirror the brain's own processing requirements, a missing step in the instructional sequence creates a corresponding break in the student's mental model. We'll build a 3-phase pipeline, starting with input and alignment, using a medical case study on auscultation. Event 1 secures attention. Before processing data, the brain must bypass its sensory barrier. This requires an external stimulus triggering an orienting reflex to prioritize the signal. Instead of starting with a definition, the professor immediately plays an audio recording of a pathological heart murmur. Without context, the anomaly creates an immediate diagnostic puzzle that the student is now motivated to solve. Event 2 informs the learner of the objective. By shifting the focus from the process of the lecture to a measurable outcome, the professor helps the student's brain filter information based on what is relevant to the final goal. In this case, the goal is precise. By the end of this hour, you will be able to differentiate between systolic and diastolic murmurs. Event 3 stimulates the recall of prior knowledge. New data strictly requires an existing neural scaffold to attach to. If the student doesn't recall the basic anatomy of a heart valve now, the new diagnostic data has nowhere to land. When this step is missed, the new information remains isolated, making it much more susceptible to the brain's natural pruning and forgetting cycles. By the end of Phase 1, the student's cognitive resources are locked in. The brain has been prepared to receive complex data without filtering it out as noise. In Phase 2, we move into processing and encoding, Events 4 and 5. Event 4 is content presentation. The objective is managing cognitive load, so data doesn't exceed working memory. We achieve this through chunking, breaking lectures into short blocks, and dual coding, using visual and auditory channels to transmit information more efficiently than text. For our auscultation module, this means synchronizing the sound of the heartbeat with a visual diagram of blood flow. The 2 inputs reinforce each other rather than competing for attention. Event 5 provides learning guidance. The professor offers mental scaffolding, strategies or rules that help the student translate the raw sounds into meaningful patterns. If this guidance is skipped, students may achieve rote memorization of the sounds, but lack the deep understanding needed to recognize those same sounds in a different clinical context. The professor provides a mnemonic or a step-by-step algorithm for stethoscope placement, giving the student a mental map for organizing the received information. Phase 2 successfully converts raw external data into structured semantic codes that are now ready for the final stage of the pipeline. Phase 3 is output and consolidation, where we shift from the student receiving information to the student demonstrating mastery. Event 6 elicits performance. To finalize the neural pathways, the student must convert their mental model into an analytical or physical action. Without this step, students often fall into an illusion of competence, where they believe they understand a concept right up until the moment they are asked to execute it. In our case study, this means students must work with a medical simulator, using their stethoscope to identify a specific pathology on a high-tech mannequin. This performance sets the stage for Events 7 and 8, which function as a corrective loop. Feedback in Event 7 must be formative. It highlights exactly where the student went wrong and how to improve. Only after this correction does Event 8 provides the final, summative assessment of their performance. The final step is Event 9, transfer. This is the attempt to decontextualize the knowledge, ensuring it isn't tied only to the classroom. The student is challenged to apply these principles to new, unscripted conditions, like different patient profiles or noisy environments, to ensure the skill is durable. Phase 3 closes the loop. By demanding active output and providing iterative correction, the instructional sequence creates the conditions for permanent, recallable expertise. This 9-step model is fractal, meaning it applies at every scale of education. The same logic used to structure a single lecture also dictates the architecture of an entire 16-week semester. The first 2 weeks represent events 1 and 2. This is the big bang of the course, where the professor must establish the global stakes of the subject to maintain long-term attention. In weeks 6 through 10, the syllabus moves into events 5 and 6. This is where the professor's role shifts from a primary source of information to a facilitator of high-density practice. By weeks 15 and 16, the focus turns entirely to events 8 and 9, validating the semester's work and preparing students to carry these skills into their careers. Mapping a syllabus this way ensures that the cognitive demand evolves over time. By shifting from passive reception in the early weeks to active production in the middle, the professor maintains the instructional momentum required to keep the learning pipeline moving. To internalize this, it helps to view the professor not as a lecturer, but as a designer of a systematic experience. Event 5, Guidance, is about creating a safe environment where the mechanics of a subject are explicitly mapped out and tested before the stakes are raised. Event 6, Practice, is the phase of iterative execution, where students perform low-stakes tasks to build the fluency and speed they will need later. Event 8, Assessment, is the final synthesis, a complex challenge that requires the student to combine all those isolated skills to solve a significant problem. When the external classroom is engineered to match the brain's internal processing requirements, the path from abstract information to professional expertise becomes much clearer. The result is a learning experience that is built rather than just delivered.